Have you ever stepped out of an elevator and noticed how perfectly it lines up with the floor? It's almost always a seamless, perfect step. It happens so reliably that we never think about it, but that perfect stop is an incredible engineering achievement. It's a feat of precision that is surprisingly hard to pull off. Think about your daily routine. You walk into a building, push a button, and wait for the metal doors to slide open. A quiet chime announces its arrival. You step inside a small, well-lit room surrounded by polished walls and a panel of buttons. You press the number for your floor. The button lights up, confirming your command, and the doors glide shut, sealing you off from the lobby. You feel a gentle lurch as the journey begins. A quiet hum fills the air as you ascend, trusting completely that you'll arrive exactly where you need to be. But behind this simple experience lies a hidden and complex problem that engineers had to solve. The elevator car you are standing in is incredibly heavy. With passengers, it can weigh more than a small car, thousands of kilograms. This heavy box is moving through a dark, vertical tunnel, often at speeds faster than you can run. Yet, its job is to come to a complete stop at a precise target, your floor, without overshooting or stopping short. If it stopped even a few centimeters too high or too low, it would create a dangerous trip hazard. It must be perfect every single time for millions of trips. So how does this machine, flying through a building, know exactly when to slow down and where to stop with millimeter accuracy? The answer is not one single thing, but a brilliant team of systems working in perfect harmony. The most important member of this team is the elevator's brain. Hidden away in a dedicated machine room or tucked inside the shaft, there is a powerful computer known as the elevator controller. This controller is the mission commander. When you press a button, you are not just completing a circuit. You are sending a request to this brain, which then calculates the best path to your destination. But a brain is useless if it cannot see. The elevator needs to know where it is at all times. For this, it relies on its eyes, a network of sensors. Think of it like driving on a highway with numbered exit signs. You know you're getting close to your exit because you see the signs for the exits before it. Elevator shafts are equipped with a similar system. All along the shaft walls, there are markers or sensors that act like signposts for each floor. A reader attached to the elevator car passes these markers as it moves. It sends signals back to the controller, essentially counting the floors as it goes by. This system tells the controller which floor the car is approaching. It's the signal that says, "Get ready, your destination is coming up, it's time to start slowing down." But knowing you're near the right floor isn't enough for a perfect landing. That requires a second, far more precise layer of sensing. It's a bit like parking a car. You use your eyes to find the right parking garage, then the right aisle, then the right spot. But for the final few inches, you move slowly and carefully to avoid hitting the curb. Elevators perform a similar two-stage process. Once the main sensor system gets the car close, a secondary set of fine-tuning sensors takes over. These might be magnetic switches that react to a metal plate installed at the exact level of the floor. Or they could be optical sensors that shoot a beam of light. As the car enters the final few centimeters of its journey, these sensors give the controller ultra-precise, real-time feedback, telling it exactly how far it is from the perfect stopping point. This allows the controller to make tiny, final adjustments, ensuring the car's floor and the building's floor become one continuous surface. So we have a brain giving orders and eyes providing information. The final piece of the puzzle is the muscle, the motor system that actually moves the car. An elevator motor isn't a simple on-off switch. If it were, your ride would be terrifyingly jerky and abrupt. Instead, modern elevators use intelligent motors with something called a variable frequency drive. This gives the controller incredible command over the motor's speed and power. Using the information from the sensors, the controller can tell the motor to accelerate smoothly, cruise at a constant speed, and then decelerate gently for a soft, precise stop. So the next time you step into an elevator and feel that smooth, satisfying stop, take a moment to appreciate the invisible ballet of technology at work. It's not one component, but a perfect collaboration. A computer brain making plans, sensor eyes watching the path, and a powerful motor muscle executing the commands with grace. This core principle of sense, think, and act is the basis for nearly all modern automation, from self-driving cars to robotic arms in a factory. It's a quiet, elegant solution to a very complex problem, performing its job perfectly, millions of times a day, hidden just inside the walls.